Okay, I think my computer's back. Hey, so this lesson, I'm not going to say it's going to be real short and sweet. All right. So I don't know how long it's going to take me to get through what I need to get through. It might not be that long. Okay. But we're going to cover, let me go ahead and start getting this set up. We are going to cover valence shell electron pair repulsion. Okay. It is a theory. Valence shell electron pair repulsion theory model. Probably should, so basically it's a model used to determine the shape of a molecule or the shape of parts of a molecule even, okay? And it's a pretty good model. It works well. Right? And we can use the model and make predictions based on what we would predict and see that those predictions are right. And some of those predictions come from using the valence shell electron pair repulsion theory. Okay, so I'm going to say that one more time. Valence shell, the valence shell, the outer energy shell, electrons, okay, repulsion, okay, theory, all right? Well, what's the theory? It's that the shape a molecule takes, actually, let me write that out for you once again. We're talking about the valence shell electron pair repulsion theory, okay? I'm going to write it. Valence shell electron pair repulsion theory, okay? And it provides a model with which we can use to determine the shapes of molecules or parts of molecules, okay? And from there we can determine the polarity of the molecules, and from there we can determine some relative physical properties of molecules, okay? And learn some more things. So this basically what this states is that a molecule will take the shape, okay, this is easy, that minimizes electron repulsions, right? That's what the theory is based on, right? That's it. So it all is, and it's determined by, so I'm going to say this, the shape is determined by looking at the number of bonding and non-bonding electron domains around the central atom. Okay, that's, or the atom that we're concerned with, right? If it's the end of a molecule, you can talk about a particular end of it. This bond right here, what would the shape be around this? But usually it's going to be around the central atom. Okay, I just think if I'm leaving something important out there. I don't think so. We're going to have, we will first determine the electron domain, and then more particularly the molecular shape, the molecular geometry. So there's the electron domain, which just counts bonding and non-bonding sites. And then within that, there are specific shapes based on how many of those sites are bonding and how many are non-bonding. So let me show you what I'm talking about. Here we have electron groups. Okay, so this is talking about electron groups around the central atom, the atom that we're focused on. So notice over here, under, let me move my picture. So I'm on the far, carbon and then the blue dot have two domains. Okay, there's two domains. The double bond site is one domain. It is one bonding site. So our two domains is, let me get red here. We've got this domain and this domain, this domain and this domain to give us a total of two domains. Now, within those, both of those domains, they're both bonding groups. Okay, I'll change the color. They're both bonding, right? And there are no domains around the central atom that are not bonding, okay? A question the student always asks is if you have something like this here, which is perfectly linear, it obviously doesn't fit in here. There is no central atom. So it's just linear. And these questions of numbers of bonding sites and non-bonding sites are, those questions are irrelevant because there's not a central atom. Okay, so just don't be concerned with that. Those are the easiest ones possible, right? And they're just that easy. So don't be concerned with that. Okay, so let's continue looking over here. Now notice here I have three domains. So that's what I meant. My electron geometry, you know, my electron groups is my very broad. It's based on the number of domains. And since they both have three, they have the same electron geometry because that's not a very specific geometry. Now more specific is the, let me get a different color, is the number within those three. Right here, all of them are bonding and none of them are non-bonding. So see, I've got the three bonding sites and I have no lone pairs around the central atom. Well, that relates to a molecular geometry that is also trigonal planar. However, if that was to change and that's too similar, if that was to change and out of my three domains, two of those domains have bonding, that would be this one and this one, and one is non-bonded. I'm going to change my color on you here. One is non-bonded, that's that one right there. Well, that's going to change the shape of my molecule. It is no longer trigonal planar, it is bent, okay? And the reason it has bent itself, is because it is minimizing electron repulsions, right? There is an electron pair right here that you don't see, okay? Right, it's right here. So what that is that's like a big Mickey Mouse pair of ears. It's a very, very dense negative charge. And it repels these electrons that are here so that they can't sit up, and it pushes those angles down, okay? So instead of being this trigonal planar and not being like this, actually what I really would rather say, so you can ignore what I just said, what I really want to say, and let me erase this right here, is that instead of this molecule being straight across, okay, it is not, it's bent. Oops. And the reason why it is bent, where's my pen? Something's going on here. Okay, let me try that one more time, guys. The reason why it is bent, it's not letting me write. Something happened. Okay, I think I got it. Okay, is because of those electrons right there. And the bonds can't go straight out, rather they are pushed down, okay? And you need to understand that. That's the theory, right? Anything that has three domains, two of which are bonding, one of which are non-bonding, will take a shape that we call bent, and it will look like this. That's it. So unfortunately for you, You have to memorize most all of this stuff. Yep, you sure do. And some of them are easy to memorize and some of them are not. I will, throughout class, I'll try to give you some tricks on how to memorize them. Some of them are the same. If you want to notice, there's another bit right here. Let's just look a little bit further. We can have 4 domains, right? There is something I need to point out here, okay? So we could have 4 domains. Within those domains, we could have all 4, we could have all 4 being bonds, and we're gonna be tetrahedral. We're gonna be 109.5. I would remember that. You don't have to memorize all of them, but you need to remember that, okay? And a couple more. You need to also remember this one right here. And then what you need to realize is that this is not 180. And it's actually going to be, notice we could just infer, never even thought about this before, that this lone pair right here, that big Mickey Mouse ears of negativity, right? Just an ear, pushes these down further than having the third bond does, right? Because right here, it's 120. Oh, actually, it puts it down less than it does. Because right here, it's 120 degrees. I told you I had never noticed that before. But right here, we have 100. Oh, crush. I almost said a bad word. We have 120 degrees. And right here, we have less than 120 degrees. Okay? So I want you to keep that in mind. Now, let me try to get back on track. If we have 4 domains, 3 are bonding, 1 is non-bonding, right? 1, 2, 3. And then there is our non-bonding Mickey Mouse here, right? So you see what happens is he essentially pushes these guys down, okay? And he's sitting there, and we have this angle going down. So we now are not at 109.5. We are more like 107.5. That is a question that will pop up, okay? What is the bond angle for a 4, 3 bonding, 1 non-bonding? Why is it less than the 4 domains, 4 bonding, 0 non-bonding, no lone pairs, right? Well, actually, I want to compare these two, okay? That's what I want to compare. I want to compare these two, and I apologize for that. I do need you to, I do apologize for that because I didn't really need to say that. We need to compare these two. So what you see here is, all right, 4, 2 bonding, 2 non-bonding. So we have 2 lone pairs. Well, they're not going to sit like this. That is not what they're going to do. They are going to sit like this, okay? So they're going to be sitting up there. And what I want you to see now is that this bond angle is going to be less, even less than 109.5. Okay. It's going to be even less than 109.5 because the presence of the two lone pairs is going to push that down even more. Okay. So what we have going on here is more like 107.5. Okay. So that's what I need you to realize. They will ask you about just the 1 lone pair in relation to just the 2 lone pairs, okay? And you need to realize when you have that extra one, it goes down a little bit, okay? You may want to memorize those. I know it's hard. It's really hard. Linear is just 180, right? Now, I'm not going to go into all of these. You can see them. You can have 5 domains around the central atom where they're all bonding, 4 are bonding, 1 is non, 3, 2, 2, 3. And that goes all through the 6s, right? We said there's a maximum of 6 domains. Notice the lone pairs are opposite of each other. You should do that as well. You should not draw this and put the lone pairs on the same side, right? Don't do that. I'm going to erase it. They need to be, they're going to repel each other. It's a repulsion theory. They're going to spread out, okay? So I need you to be aware of that. Notice the lone pairs are here, right? Everything is spread out as much as possible. You see everything is spread out. Everything's spread out. Here you have the 2 lone pairs. This is a T shape. You can see why, okay? This one pops up. I see that one pop up a lot. I see this one pop up a lot, okay? Notice that we ended up with 6 extra electrons after we satisfied everybody, and we just placed them just like that. This is going to be a non-polar shape, okay? This is going to be a non-polar shape. You guys should write this down. I'm telling you right now. I'm going to branch off that this is going to be a non-polar shape. Even though there's those electrons there, I might be wrong. Need to look that up. This is going to be a non-polar shape. Let's see, is BRF, we'll have to look that up. I'm going to look up. Curious with this right here, I think we probably have a little polarity going on here. So I think I jumped the gun right there because nothing is here to cancel this dipole, okay? And I want you to think about it like that. There's nothing here to cancel this dipole. Lone pairs do not cancel dipoles. It drove me crazy for years. I finally just figured it out. Okay, lone pairs don't cancel dipoles. Just accept it, move on. This is a non-polar shape, assuming that these are the same atoms, because this cancels this, okay? This is a non-polar shape because this dipole cancels this dipole cancels this dipole, this one cancels this one, and this one cancels this one. So what I need you to realize right now is when the dipoles cancel, you have a non-polar molecule, okay? And you have to write that. Explain why it's non-polar. The dipoles cancel. That's it. That's it. The dipoles cancel. That's why it's polar. Okay, even though it has polar bonds, the dipoles cancel. That's all you got to say. This dipole cancels this dipole, and this dipole cancels this dipole. Okay, but you see here, he cancels him and he cancels him, and there's really, they might cancel each other. You're not going to be faced with that one, but I'm going to put a big question mark, and one of you guys is going to look it up, and you're going to bring it to class, and you're going to tell Miss Murphy. Okay, thank you. And I'm not going to worry about it. Now, this right here is most definitely going to be a polar shape, okay? And you should see that. You should see that these dipoles cancel, these dipoles cancel. There is nothing here to cancel this dipole right here. Once again, the negative charge non-bonding pairs do not cancel the dipole. They don't cancel the dipole, okay? Confused me for years. Now, if you look at this, you question yourself, is it polar or not polar? But if you look at the way it's shaped, you see that this sucker should be polar, right? Boom, 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 boom. All right, so we would give this a polar shape. This here looks non-polar, very much so. This shape bent is polar. The dipoles do not cancel. So another thing, if you are asked, why is it polar? The dipoles do not cancel. You got the credit. Of course, you got to draw it correctly, right? And then from there, you say, well, the dipoles do not cancel, it's polar, or the dipoles do cancel, it's nonpolar. Okay? That's simple. And any trigonal, anything that has this shape right here is polar. Okay? These can be both, all right? But typically they're going to be nonpolar. When that's not the case is when these atoms are not the same atom. Then the dipoles may not cancel. We looked at an example like that in class. If you'd like to give you another example, write it down and bring it up in class, and I'll be happy to do it, okay? More than happy. It would be a great addition to the class is someone to bring the questions. Some of you have, I think that's great. Remember, we need to look up bromine, five pentafluoride. Someone bring that to class for me, please. And you remind me because I'll probably forget. And that's it. But unfortunately, you need to know these. Let's finish this. This is bent, definitely polar. Okay. This is trigonal planar. Assuming all of these are identical elements, your dipoles will cancel. That is non-polar. And, you know, this can be, but all of these guys, you've got to make sure that the terminal atoms are the same. Otherwise, my polar, non-polar, polar, non-polar, it's not, you know, it's not wholehearted. It's just when all of them are the same, okay? Because right here, I'm going to say non-polar because, right, they are the same. But if I have an HCN, I have a different situation because this polar bond points that way and this polar bond points that way. So I have a polar. So you've got to be careful when the terminal atoms, those atoms on the outer edges, are not the same. Just if you need a question, if you don't understand what I'm saying, ask me. And ooh, that's good. I'm going to be able to go ahead and end this lesson. Okay. So stop and end.